Mod-Arg Form is it's an alternative way of describing the position of a number. What we're using is Cartesian coordinates. Another name for Mod-Arg Form is what's called polar coordinates. So modulus is simply the length of the vector, oh, there's the word, the vector OZ. Now, there's the point, x plus iy, so we know it's Cartesian coordinates, x and y. But the other way we could describe it is the length of the vector. A simple way of saying that is how far away is it from the origin. We could use Pythagoras to work that one out. Hypotenuse is, of course, and there's that thing, x squared plus y squared. Phew, I no longer have to keep saying x squared plus y squared, oh, real part squared plus imaginary part squared. I can now say modulus squared. So x squared plus y squared is the modulus squared. Its symbol is the absolute value symbol, because that's what absolute value means, if you remember. Distance from the origin. Now, obviously, we've only been dealing with real numbers, but modulus and absolute value are basically the same thing. When you were finding the absolute value of a number, you were actually finding its modulus. So there we go. Modulus is z, square root, real part squared plus imaginary part squared. Now, obviously, there's more than one point that would have that modulus. In fact, that would lie in a circle. So to talk about a specific point, we need another piece of information, and that piece of information is the argument. And the argument is the angle that the vector, or the hypotenuse of this triangle, if you like, makes with the positive side of the x-axis. Again, much like we did in coordinate geometry, we said one of the ways of working out slope was to find the tan of that angle. Same angle we're talking about. So that one in there. Very creative symbol for argument, arg. ARG. So it would be, well, whatever angle gives us the tan ratio, y on x, imaginary on real. And then now we have a unique set of numbers that will define it, because each individual one would have its own set of modulus and argument. So there is only one point that would be, say, 2 units away from the origin and make an angle of 45 degrees with the origin. We, for the sake of definition, restrict the angle, because angles go around and round and round and round and round. So we don't want multiple answers. So we always give our answers in between pi and minus pi, or 180 and minus 180. So positive angles and negative angles. So 4 minus 4i then, well, the modulus, square root of 4 squared plus minus 4 squared, which is 4 root 2. Argument. Now, you may find it useful to draw a diagram, and I know how you love drawing diagrams, because whilst that's the inverse tan of minus 1, it might not be. Because if you go to your calculator and go inverse tan of minus 1, it'll only give you one answer. But there actually are 2 possibilities, because tan's negative in the second quadrant and also the third quadrant as well. So we need to know which quadrant we're talking about. So the imaginary part, and that's why I say I like to draw a diagram sometime, imaginary part is negative, real part's positive, so I know I'm over in the 4th quadrant. So I'm talking about a negative angle because it's below, and it would be an acute angle because we're always starting from the positive x-axis. So it's minus pi on 4. Minus pi on 4 for that one. Which now means we can rewrite that number, instead of being 4 minus 4i, which is the number when we're referring to the Cartesian position, we can now write it in terms of the modulus and argument. So x plus iy, referring to Cartesian, but it becomes this, r cos theta plus the imaginary times r sine theta. Because if you were to draw up a triangle, you could do it via trig. You can simply say, well, x over r is equal to sine theta, cos theta, and so on. So factorises r. This brings up an abbreviation that you sometimes see. Instead of writing cos theta plus I sine theta, a lot of times you'll see it abbreviated as just cis, because the angle is always going to be the same when we're talking about a particular number. So rather than writing cos plus I sine each time, often they write cis. But you don't want to get confused with cos. So make sure it's cis or cos. Which one is it talking about? So r cis theta, and r is the modulus, theta is the argument. 4 minus 4i would be 4 root 2 cis of minus pi on 4. Root 3 plus I, so modulus is 2. Argument, well they're both positive in this case, so I know I'm in the first quadrant, got to be an acute angle. Acute angle would be pi on 6. So 2 cis pi on 6. If we want to go back the other way, well remember cis stands for cos plus I sine. So it's 6 times the cosine of pi on 6 plus I times the sine of pi on 6. Pi on 6 is 30. So cos of 30 is root 3 on 2. Sine of 30 is a half. So there's our number, 3 root 3 plus 3i. So relationships. If we're going to use these numbers, but in a different form, we need to know how to add and subtract and so on. Now, when we multiply modulus, we can do it in any order, it doesn't matter. So you can find the modulus first, then multiply, or multiply, then find the modulus. However, the argument is different. It's much like logarithms, if you think about it. When you multiply, we actually add the arguments together. And that comes back to that idea of rotation before. Because when we rotate, or multiplied by I, we rotated 90 degrees. Well, I, if you were to write that in Mod-Arg form, is cis pi on 2. So you're actually adding the argument of I onto it. So you rotate a pi on 2. Okay, so multiplication rotates Z1 by Z2. Proof. Here we go. So Z1 is R1 cis theta 1, Z2 R2 cis theta 2. I'm going to need to write it in its full form to do this, so set cos plus I sine. Multiplying, well the R1 times I2 is easy, trig's a little bit trickier. I get cos minus sine for the real part. That's familiar. And then for the imaginary part, I get sine cos sine. Hang on. Cos, sine. If it's not the sine, it's not the sine. And the other one, sine cos sine. If it's the sine, it's the sine. So we've got cos theta 1 plus theta 2, I sine theta 1, which is proven, hey, when we multiply, we add the arguments together. How cool is that? Of course, it follows that if we have several things multiplied, we do each bit individually. But if we're argument, we'd be adding each bit individually. Okay, division, pretty much the same. You divide first, then find it, but again, like logarithms, when we divide, subtract the arguments. So if I had something like this, I wanted to find the modulus of Z1, Z2 over Z3, Z4. I could find the modulus of Z1. I could do each bit individually, multiply the top ones together, multiply the bottom ones together. That would give me the answer. But when it came to the arguments, whichever ones are on the top, I'd be adding, and whichever ones are on the bottom, I'd be subtracting, because that's a division. And the third thing then, Z to the power of n, it'd be the same as modulus of Z to the power of n, because if you think about it, Z to the power of n is Z times 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 Z, how many n is. But we just said that's the same as mod Z times 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 mod Z, and so on and so on. Whereas with the arguments we're adding, so the argument of Z to the power of n would be argz plus argz plus argz plus argz plus argz. So we'd have n lots of them. So n lots of argz. So if I wanted to find the modulus and argument of this, sure, I could multiply those two numbers together, divide by the one at the bottom and work out the number.
Or you can just find the modulus and argument of each and then do what we just did.
Okay, sounds like a plan. So, the first one, 5 squared plus 1 squared is?
26.
Very good. Next one, negative 2 squared plus negative 1. And 26 times 5?
No. Yeah, it is.
3 squared?
13.
Oh, wasn't that lucky? And 13 goes into 26.
So root 10.
Oh, wow, that was lucky. Unfortunately, the argument's not quite as nice. Oh. I'm going to go back to degrees for this. Okay, 11 degrees 19. Now, -1 on -2 is just to remind me that, hey, I'm actually in the third quadrant, not the first quadrant. So that would be negative an obtuse angle, 153 degrees 26. And tan 2/3, 33.41. I end up with -175.48. So if I wanted to work out the actual answer for that, I could now go, root 10 times the cos of that plus I sine of that. Might not be an exact answer, but I could get an approximation. Okay.